All right, so good afternoon and thank you all for joining us for our webinar today as we take a closer look at the touch points along the digital thread, following a PMI workflow from process analysis back to design. Today we are joined by Jeff Folds, Director of Business Development, and Ms. Murray Desaunay, CEO at Origin International. We are also joined by Jennifer Herron, Founder and CEO at Action Engineering. Finally, we are also joined by our CAD MicroSolutions team members Rob Johnson, Director of Metrology, David Lee, Application Specialist, and Kristen Waters, our Digital Manufacturing Technical Manager. We hope you've come with questions for us today. As usual, we'll save some time at the end of today's session for a question and answer period. So feel free to type your questions into the panel as they come up, and we'll do our best to get to them at the end of the webinar. Today's webinar will be recorded and we'll be sending you the recording via email tomorrow. So if any questions arise afterwards, you can feel free to respond to that email and we'll be in touch shortly. So without further ado, I will pass things over to Rob to get us started.
Thank you, Sarah. Good afternoon, everyone. Thank you for joining us today for our presentation on touch points along the digital thread. We've gathered 4 industry experts to illustrate and discuss how PMI information is applied and used throughout the design, manufacturing, quality, and analysis journey. You'll be seeing a shared part shared across all the groups to keep the theme the same. I'd also like to thank the additive team at CAD MicroSolutions for 3D printing the part today and demonstrating how additive manufacturing can be used to verify processes before going into production. While traditional presentations typically start with the design engineering aspect and working downstream to manufacturing, we've decided to flip the process to show the importance of implementing PMI on all your models correctly. Throughout the presentation, there'll be a few polls asking for your input along the way, and we'll show you the results of those throughout the presentation or at the end of the presentation. So let's get started. I'd like to introduce Jeff Folds from Origin International. Over to you, Jeff.
Okay, thank you, Rob, and good day, everyone. In the next 10 minutes, Cecil DeLine and I are going to show you how the digital thread helps QA automate manual tasks and deliver more value to manufacturing. We're going to do this in 3 stages. First, there will be a brief company profile. Second, we'll review the workflow from several different perspectives. And third, we'll show some examples of the reuse of MBD in QA with Checkmate for SOLIDWORKS. So let's go to step 1, which is a little bit of the story of Origin. We make the Checkmate add-in for SOLIDWORKS. It's a set of unique tools that engineers use to solve dimensional problems in automotive, aerospace and defense, medical devices, and oil and gas. We've been doing this for the better part of 25 years. Second, let's consider the workflow. People tend to think of this as a one-way flow from design downstream through manufacturing to inspection. Today, though, we're flipping the script and we're starting with inspection and working upstream through manufacturing to design. The reason that we did this is that dimensional problems tend to get blamed on QA. And while it's true that the costs of delays and scrap and rework can be pretty painful when QA says that a part can't ship, oftentimes the problem really originated someplace else. Often the real issue is that product manufacturing information, or PMI, needs to move freely among design, manufacturing, and inspection, and it doesn't. And when I say PMI here, I'm using it in the broad sense of both the annotations that go on the CAD and the inspection results that come back from inspection devices like GOM scanners. So there are many ways that the information is constrained. For instance, computers have to wait for people to translate PMI into a form the computer can understand, and then input it into the computer system before it can do its job. MBD really removes this constraint because it's PMI that computers can read and people can read too. So manual processes can be automated and done well. MBD pays for itself and adds a tidy profit as well. If you visit QA or you work there, you're probably familiar with these manual processes that are needed to consume PMI. It takes a lot of expertise and time, which really brings me to the third part of our demo, which focuses on the cast machining process, and in particular this pump housing, cast pump housing, prior to machining. In a moment, Cecil is going to show you how this works out in Checkmate in 3 different ways. First of all, he's going to show how you can reuse PMI from design and from GOM, and in fact work with GOM scan results directly inside SOLIDWORKS. Second, he's going to show you how Checkmate automates feature tracing and reporting and other tedious manual tasks. And third, he's going to show you how Checkmate automates the setup and bookkeeping needed to simulate solutions to dimensional problems inside Checkmate. Now, one bit of full disclosure, we substituted a 3D printed part for the cast blank. And frankly, if we'd used a cast blank, more features would have been good at this point because of the 3D print quality not matching the output of the casting process. So to show the workflow, the tolerances needed to be relaxed, which we've done. However, the workflow itself is still 100% reflective of what you'd experience if you were working with the cast blank. So now over to you, Cecil.
Good day, everyone. I'm going to show how Origin's Checkmate for SOLIDWORKS links inspection to the digital thread. We do this by consuming the DimXpert MBD and driving it through the metrology and dimensional problem-solving processes. On the screen, the SOLIDWORKS DimXpert tree containing the MBD appears on the left. In the center of the screen, the MBD is shown graphically on the CAD. And over on the right side, you'll see Checkmate's browsers. The first you'll see in action is the programming browser. First, Checkmate processes the STL file that CMS created with a GOM scanner and extracts a color map. Next, Checkmate consumes and reuses the MBD to develop an inspection plan. At the same time, Checkmate also extracts all the actual data from the color map. In a moment, I'll show you how you use Checkmate to get value from all this data. That's just as soon as I draw your attention to all these yellow lines on the CAD. These are the measurements that Checkmate created using the MBD to construct and then extract from the GOM scan. There are hundreds of features on this part and thousands of measurement points. Why so many on a relatively simple part? It's because more complex parts are common, requiring this level of measurement, and permission to show them is very uncommon. You can burn hours moving data from the apps QA uses to the apps that manufacturing and design use. With MBD, we moved all this data from GOM to Checkmate for SOLIDWORKS in the time that it takes to make a pot of decent coffee. And we've reused the MBD to generate all the feature nominals for the appropriate tolerances, including the balloon numbers. So when you need to generate reports, in this case, a first article inspection report, you have 100% traceability back to the DimXpert CAD annotations, and there's no time loss to rekey numbers. Now, as Jeff said, manufacturing may need to iterate through many dimensional problem solutions to find the best fix. You're going to need a metrology expert to set up the data in their own datum reference frames and help process it. The bookkeeping for the trial scenarios is really tedious. To help out, Origin added a new utility to Checkmate. MBD annotations enable Checkmate to set up the analysis framework and populate it with all the measurements. Checkmate also gives a first cut of a best fix solution. It's the GeoTol Manager, short for Geometric Tolerancing Manager. All of the results are instantly organized into their datum reference frames. Looking at the highlighted features, the deviation column shows how much these features were out. The features are green though, so Checkmate found enough bonus tolerance in the datum structure to declare that the features are in. The browser also shows how much bonus tolerance was used. We'll have more to show about the GT Manager on our next webinar with CMS. Back to you, Jeff.
Thank you, Cecil. That was great. Before I hand things back to Dave and Sarah, I want to take a moment and review the 3 key takeaways from Cecil's presentation. First of all, with MBD, Checkmate is able to reuse the full spectrum of PMI, whether it's coming from CAD annotations or scanning devices like GOM or other inspection equipment. And what that does is it enables QA to work a lot faster. With Checkmate, you can eliminate tedious and error-prone setup and bookkeeping tasks for feature characteristic tracing, analysis, and reporting. Just bear in mind that all of the reuse of that GOM scanner information and the MBD took us about as much time as it took to make this presentation, or the time it makes to make a decent pot of coffee. And without MBD, that would have taken hours and hours of work. And finally, with Checkmate, it provides a framework that enables you to simulate best fixes for dimensional problems in SOLIDWORKS, which means that it's much easier for manufacturing to come up with solutions faster and with less work. So thank you very much. As I said, I'm going to turn things back to Dave now, and he can walk you through the process for creating these scans with GOM. And Sarah may actually have a quick question that she wants to ask. So if you've got a moment, you can just click the radio button beside the choice that you're using for doing your measurements right now, and then we'll be able to give you some results on the fly from what everybody's experiences are with measurements in their companies at this stage of the game. This was another poll question that we were hoping that people might be able to provide a little bit of feedback on in terms of where your company sits in the ecosystem, whether it's on the supply side or on the assembly side. And once again, we'll be able to provide you with the answers to the summed up answers from everybody's responses by the end of the webinar.
What's going on?
All right, so thank you, Jeff, for the introduction. Good afternoon, everyone. My name is David, and today I have the pleasure of taking you through the portion of the webinar where we'll cover 3D inspection using 3D scanning technology offered from GOM. So in this portion of the webinar, we'll first introduce GOM as a company. We'll then talk about the different solutions and technologies that they provide from both a hardware and software perspective, and then discuss how exactly we can leverage GOM's 3D scanning capabilities for the purpose of 3D inspection in order to check the quality of our parts and assemblies. So to start off, GOM is a German optical metrology company that is operating under the Zeiss Group, and they provide contactless, accurate inspection capabilities through 3D scanning technology that makes use of specialized camera setups and blue light fringe projection. So this method of scanning and measuring is known as optical metrology, and it offers rapid, high-resolution capture of data. And just to provide you with an example of the speed at which we can obtain the data, using the setup shown in the picture on the left, we were able to arrive at a full 360 scan of the white part within a span of 10 minutes from the first scan. So once we collect the 3D scan data, we can then use it in the GOM Inspect software to calculate the measurement results we want to see, whether we want to check for dimensions, positions, GD&T characteristics, thicknesses, and much more. And once we have the results of the inspection, we can have this output back to the digital thread for further processing and evaluation of the part. So now let's talk about the system configuration of the components that make up this scanning solution. So first we have our ATOS Q 12 megapixel sensor that's installed with a 500 millimeter measuring volume. And this is mounted on our manual stand that we can use to reposition the sensor as needed. This is combined with our automated rotation table that's synchronized with the sensor to rotate the part following each new scan position that it brings us to. And this is connected to our laptop that's running GOM Inspect Suite for overall system operation. And on top of this, we also use reference points that are placed on the table and the part for tracking, as well as to combine separate scan series that we take of the part. And in order to capture the full geometry of this part, we needed to scan it in 3 different positions on the table. And we'll talk about how we managed to combine that data later on in this presentation. So here we have a video showing the setup that we used to scan this part, and we can see the ATOS Q sensor projecting a blue light fringe projection pattern on the surface. Now, based on how this projection pattern deforms according to the surface geometry and using known dimensions from the sensor, we're able to reconstruct a detailed 3D point cloud of the data by the left and right hand cameras capturing millions of points with each single scan. And here we see in the software view a live camera feed coming from the sensor, and we also see the scan data being updated in real time with each new scan. And the way that the software is able to position each new scan is through the use of the reference points that are used for tracking, as I mentioned earlier on. So now that we've completed scanning the object in its first position, we now need to reorient the part on the table into its second and third positions to capture the remaining geometry. So once we've done this, we will combine all 3 individual scan series into a single uniform mesh. So here we have a video showing the object being scanned in its second position with the same setup of the ATOS Q and the rotation table. If you take a closer look at the object, you will also notice that there are some reference points placed around the surface of the part. And the reason we have reference points on the part itself is so that when we go to combine the scan series, the software is able to complete this task by recognizing at least 3 common points that exist in all 3 of the separate scan series. And using those 3 common points, it's able to transform the data into one another and combine everything that we've captured so far to form a single uniform mesh. So we're now back in the software view, and you can see each of the different scan series there that we took of the first, second, and third positions of the part respectively. And we're going to quickly see also the data that's been captured in each of those different positions. So the reason why we had to use 3 positions was so that we could capture all of the relevant data that we need in order to measure the parts with the dimensional requirements that we have set. And now that we are satisfied with the data that's being collected, all that's left to do is to combine them into a single source through the use of the polygonization tool here, which will transform our preliminary 3D point cloud data into a uniform smooth mesh profile. So this process usually takes about a minute or 2 to complete. And once we have finished up with the polygonization, you will see that the mesh is now a complete uniform data entity that has all of the separate geometries and overall scan data that's been captured in each of the separate scan series transformed into one. So with this complete data set, we can now use this as the basis of our inspection methods for further inspection and analysis of our part. So now that we're familiar with GOM's 3D scanning technology and the type of data that we can obtain, how can we leverage that data for the purpose of inspection and to check the quality of our parts? Well, in GOM Inspect, once we have these 3D scan data of the part, we can load it into the software and perform a measurement analysis. And the way this is conducted is by creating different inspection elements in the software according to the model itself. So whether we want to check for different dimensions across specific features, we want to apply GD&T characteristics and apply tolerances. If we want to analyze the thickness at different regions and even cut cross sections at different locations, we can do that all directly in the software. Now, if we wanted to take it a step further and automate certain processes, such as manually creating each of these characteristics, we can use SOLIDWORKS MBD and GOM Inspect Professional to achieve this for high volume and rapid throughput applications. So the first process would be to go into SOLIDWORKS MBD, where we have our CAD model, and then embed all our critical product manufacturing information directly in a step 242 file that has all of the inspection characteristics listed inside. Now with this step 242 file, we can load that PMI enriched CAD file into GOM-INSPECT Professional, where the software will automatically create all the inspection elements we would normally have to do manually one by one, therefore saving a ton of time coming from the design workspace in SOLIDWORKS and all the way over to our inspection workspace in GOM-INSPECT. So let's take a quick look at the overall 3D design to 3D inspection process. So first, we use SOLIDWORKS to draft up the model and also apply our MBD information. We then export out the MBD CAD file in the form of the step 242 file, load it into GOM-INSPECT, and have all our inspection elements created for us. And then the last step of this 3-step process is to simply scan the part, bring in our mesh data, align it to our CAD model, and then calculate all the different inspection elements we've set from SOLIDWORKS MBD. So this helps save so much time because you don't have to manually recreate any kind of inspection element or geometry that you would normally do in GOM-INSPECT. All of that is taken care of directly from the SOLIDWORKS MBD plugin that we used earlier on. So now let's take a look at it from a live software point of view. So here we have our 3D scan data being brought in to GOM-INSPECT. We have this loaded up, and then we're basically going to go through that 3-step process of first going into SOLIDWORKS MBD, and then exporting out the step 242, and then bringing it into GOM-INSPECT, aligning the data. So here we have SOLIDWORKS opened up with the part that already has all the MBD that we need to see applied to each relevant feature. I'm now exporting this data as a step 242 file where it will go ahead and directly embed each specific characteristic that you see here into the relevant features so that we have an intelligent step file that we can use in GOM-INSPECT. So right now it's going ahead and processing that data, packaging it all into a single source. And once that's completed, we will now have a step 242 file with all this information that we can readily use anytime. So now let's switch back over into GOM-INSPECT. I'm going to load in the step file with the PMI that's been included. I'm going to add it to this part. And you'll see as soon as it comes in, all these different annotations and different characteristics being listed already in GOM-INSPECT. And each of those will be created directly on the CAD model itself. So whether we want to check for a plane's flatness or the diameter of a hole, it will reconstruct all the geometry such as a cylinder or a flat plane on the relevant features and apply that dimensional characteristic to it. So now that we have brought in the CAD data, you can see in our inspection explorer, we see all the inspection characteristics being listed and categorized as we saw it in the left-hand side. So we see our GD&T information, we see all of our dimensional information, we see how they link to specific features on our part, and we can see the nominal values or the perfect values that are being read directly from the CAD model itself that we can compare to later on with our actual scan data. And in addition to that, we also have things like relevant datum systems that's also been brought in from MBD that we can use for alignment purposes and so forth. So now that I've completed the alignment between our mesh and the CAD, you can see the overlay there. And now if I turn on the visibility of some of these different inspection elements that we saw earlier, you see now instead of the question mark being shown in the actual column, we now have actual values being populated and a deviation between the nominal and actual values, which are calculated from both the CAD model and the actual scan data respectively. And we can also see this listed in a table format if we wanted to get an overall view of all the different inspection results that we saw. So now that we've gone over the measurement and inspection process of the digital thread, we'll then transition into how we can leverage PMI and other data in order to manufacture our part. And to do this, I will transition it over to my colleague, Kirsten Waters, to present that material.
Thanks, David, and thanks to everyone who's joined us today. Next, let's hop into the world of manufacturing. I'm going to be showing you guys SOLIDWORKS CAM, specifically the tolerance-based machining module inside SOLIDWORKS CAM. So just a quick recap, SOLIDWORKS CAM has been available inside SOLIDWORKS since 2018. And if you're a SOLIDWORKS user using 2018 or higher and you're on active subscription, you have access to SOLIDWORKS CAM add-in at this very moment. What is SOLIDWORKS CAM as a CAM solution? It's based on intelligent, knowledge-based machining strategies. This software is going to identify machinable features. It's going to suggest machining strategies to us based on our company's best machining practices. So these three buttons up here, extract machinable features, generate operation plan, and generate toolpath, are going to speed up our programming capabilities by roughly 80%. And we're going to be able to store all of the information on what strategies or sequence of machining operations that we want to apply to what machinable features. And we save all of this information back to a technology database that's running in the background. So how does TBM, or tolerance-based machining, come into play? TBM is going to perform these same core functions, and it's going to use the exact same feature recognition software, but it's going to focus on recognizing the linear symmetric and asymmetric tolerances along with GD&T data, and it's going to call forth specific machining strategies we would want to apply in order to maintain these tolerances and to have our part have the best chance of passing QA inspection. So let's hop on over to SOLIDWORKS CAM TBM, and let's open up the tolerance-based machining settings. So I'm working with an imperial part right now, so I want to start with my tolerance range mill. You can see here, this list of features is all of the different prismatic features that TBM is going to be able to read tolerance information off of. This middle column here is all of our default strategies. So without taking into consideration the tolerances, what default strategy would we want to apply to each specific feature? And then the right-hand side is going to identify the number of tolerance-based conditions that we've created and saved for a particular type of feature. So let's look at hole. Now, if we're dealing with a hole with no tolerance data, we probably would go ahead and drill that hole out. We'd use a center drill operation followed by a drilling operation. But if we've got a tight tolerance on that hole, let's say 0 to 1,000th, we might want to approach it with a different type of machining strategy. We're not necessarily going to go ahead and drill. Maybe we're going to bore. Maybe we're going to ream. And really the onus traditionally has been on us as CNC programmers to determine what is the best machining strategy to apply based on a tolerance. Well, TBM really automates this process for us. So we can create different tolerance ranges depending on the type of feature. And inside of these tolerance ranges, we have the ability to select specific strategies. So TBM has the capabilities to recognize both negative mean tolerances, nominal or 0 mean tolerances, and positive mean tolerances. And we can kind of tweak it even further and apply a specific strategy based on those tolerance ranges. Inside of the tolerance range, if I wanted to adjust the ranges, it would be really easy to do so. So we have this Edit Tolerance Range button at the bottom, and we have the dialog that pops up, and we can simply add in additional values as we need to. Pressing this plus button is going to add them into the list in their correct position, and we could just go ahead and keep adding in values and creating new tolerance ranges. In terms of the strategies, if we wanted to change a strategy for a particular range or a particular type of tolerance, we could just go ahead and select from the drop-down list, and all of the different strategies that we have saved in our TechDB become available. So we could simply go ahead and select an alternative strategy if we needed to. The next tab that I wanted to show you guys was the GD&T Mill Inch tab. So once again, all of the features listed on the left-hand side are features in which TBM will recognize GD&T data off of. In the middle, we have our default strategies, and on the right, we also have those tolerance-based conditions. So as I click through the specific strategies, I can see here, I have the symbol, the GD&T symbol that I want to apply. I have the tolerance range, and then I have the specific strategy I want to apply based on that tolerance range and based on the type of GD&T information. I could also edit really easily. So this opens up that range dialog box, and here I can select the type of symbol. So we have access to all 14 symbols. And then I could go ahead and I could create new tolerance ranges as I needed to. And once again, it's just as easy as entering that number and pressing the positive add button. So let's hop on over to our tolerance-based machining run command inside of our TBM command manager. So when I click this button, I'm given the option to recognize the tolerance range if I want to. If I had any ISO 286 limits and fits, I could also recognize those on this part. I can also recognize multi-surface features based on a particular surface finish. So I could create ranges of surface finishes from, let's say, 0 to 50, 50 to 100, 100 to 150. And for those 3D surfaces, I could apply specific 3-axis operations, including specific pattern types and specific operation parameters for those multi-surface features. This last button here gives me the option to recognize the GD&T data, and if I wanted to, I could override the dimensional tolerance range and ISO 286. This next tab over is where I can go ahead and I can click Extract Machinable Features. So this is going to run that automatic feature recognition technology. Not only is it going to find all of the prismatic features on my part, but it's going to find the individual mill part setups. So those 2-axis planes in which our tool movement is based off of. And it's really quickly going to tell me if I wanted to machine all sides of this part, how many individual mill part setups would be required. So with one click of the button, we've got 5 different setups that have been generated, and the software has automatically generated and sorted those machinable features across those 5 different setups. The next button over is that GD&T button. So here I can see that I have one circular pocket strategy, feature that has been recognized with a specific GD&T tolerance range. So if I click on that button here, I can see that one of the callouts on my part has a profile of surface callout applied to it. It falls within my 0 to 0.02 inches tolerance range, and the strategy that I'm going to be applying, if I choose to, would be a rough finish and then bottom finish strategy. So if we want to apply this, we can go ahead and select this Apply to Identified button. And then I can see on the left-hand side, this circular pocket under Mill Part Setup 1 has been updated with a rough finish, bottom finish strategy based on that profile of surface callout in the 0 to 0.02 inch tolerance range window. So I'll go ahead and press OK. And for this demonstration, I'm going to go ahead and generate the operations for that particular feature. So I'm going to right-click and select Generate Operation Plan. Now I have that one mill part setup that's been generated with those 2 operations. I'm going to right click once again and I'll generate the toolpath for that setup. And let's go ahead and simulate for this circular pocket. So we can see here that our GD and callout is at the bottom. And we're going to go ahead and from our SOLIDWORKS CAM command manager, we're just going to go and press Simulate Toolpath. Now I'm going to tweak the speed a little bit, and I'm going to go ahead and press that play button. So the first thing we're seeing is that roughing toolpath, which is using a 3/4 inch end mill. Next, we're coming in with our finishing toolpath. That contour mill is using a 3/4 inch hognose. It's automatically identified the bottom radius of the circular pocket, and it's selected the appropriate tool. So a hognose tool with a 0.1 inch corner round on it. So now we've finished milling that circular pocket. Let's go ahead and press this Show Difference button so that we can display the difference between the machined features and the target part. So as you can see here, this area of the circular pocket is all appearing in green. And that means that it has cut to zero tolerance. So if you see on the top left corner, areas of red indicate overcut areas, and areas of blue indicate undercut areas. So based on the strategies I've applied, we look like we're good, and this circular pocket, would be cut to spec. Let's hop into a PowerPoint to review the benefits of tolerance-based machining. So the main benefit, as I mentioned before, traditionally, the onus was on the CNC programmer to interpret the 2D drawing to make a note of those specific tolerances as set forth by the engineer or designer, and to be able to apply specific machining strategies and operations to be able to meet those tolerances. But now we can streamline that design to manufacturing process. Programmers can leverage the PMI data that already exists on their 3D model, and they're going to be able to instantly generate tolerance-specific toolpaths without having to interpret those 2D drawings. So this is dramatically going to reduce the time required to generate these CNC programs for parts with both close tolerances and surface finish requirements with this rule-based machining, along with our knowledge-based machining. A benefit from that would be to reduce scrap and rework from human error, miscalculations, and inappropriately applied toolpaths. Another thing to note, if the tolerance specification of a feature changes, SOLIDWORKS CAM is automatically going to update the machining operations using these predefined rules. And last but not least, this technology comes free with all modules from SOLIDWORKS CAM Standard all the way up to the highest CAMWorks bundle, which is CAMWorks Premium. So I hope from my presentation that everyone can now see the advantages of using TBM in conjunction with the PMI. I would like to now introduce Jennifer Heron from Action Engineering, and she'll be highlighting the gaps between CAD CAM and inspection. Thanks for watching.
Thank you, Kirsten. Hello all, I'm Jennifer Heron, CEO and founder of Action Engineering. At Action, we have a team of MBD coaches who work with organizations, both small and large, to evolve their drawing-based practices into smart model-based practices. I'm glad to take the handoff from tolerance-based machining to share how I created the smart tolerances that make such a big difference in the manufacturing and quality phases. Now that you have seen the end state of this pump case and the in-between processes and where the major cost savings come from in the digital thread, I want to show you how I created the data to support it. And hopefully by the time I'm done, you will understand why the authoring phase is so important to being able to realize the enormous cost saving opportunities in manufacturing and quality. It is, of course, true that we do not just build parts, but really we build assemblies. So here is how the pump case fits together with its mating parts. And notice that we've specifically chosen the datum reference frame for the pump case using the context of the full assembly. So the cover mounts to the pump case via datum feature A, and the impeller spins inside the pump case on datum feature B, and then the entire assembly is mounted on the surfaces that are qualified by a profile tolerance of datum feature C. Now, I'd like to get more specific and down to the original data requirements for the digital thread and actually how to author it. Looking at the internal cavity now of the pump case, I can select the geometric tolerance button. I'll select the profile symbol, type in the tolerance value that I want, and then identify our datum reference frame. I select on the surface. I want to just use that one single flat surface, so I identify that. Click on the window and then click OK. Now I want to show you how to create balloon number 29. This is a manual step that requires that you type in the symbology before the tolerance frame. And then that is what told the quality software, the inspection software, which characteristic that is, and we can follow that digital traceability all the way through. Let's look at one more set of annotations to give you a little more exposure to using DimXpert annotation tools. The holes were created using the hole wizard and a pattern, which gives us the digital element details needed to properly author the pattern threaded holes. So I've selected one of the holes in the pattern, clicked it. You'll notice that it automatically counted 7 holes, so you don't have to do any adjustments there. I'm adjusting the tolerance of the thread depth that I want. And then what I'll do is come back after that annotation, add the positional tolerance, identify that I want a tolerance of 10 thousandths. I'm going to add the diameter symbol because it doesn't do that for you automatically. Then I'll identify the datum reference frame that it refers to. Now we click on the 7 times 832 annotation, place that, say OK, and it'll automatically pop to it. And now you have your set of annotations that identify that whole pattern, and it includes all the digital information needed to identify that thread. Then we go ahead and add balloon number 27 to identify the threaded holes in the bill of characteristics, and a balloon number 28 that captures the positional tolerance requirement of the hole pattern. And now you've seen how the data was authored to support both tolerance-based machining and digital inspection. Now that we've reached the end of documenting the completely tolerance part, I like to double check my work. So I use the Tall Analyst button because it shows me which surfaces are digitally constrained with a tolerance. The surfaces in green are defined, and the only surfaces that remain undefined are the break edges, and that I'm pretty comfortable with. So using Tall Analyst always makes me feel much more confident that I have a fully defined part compared to kind of my wishy-washy confidence level when defining tolerances on a drawing. This part is now ready to pass off to the shop floor because its digital elements are ready to be read by machines and trusted by humans. Now that the engineering is ready to go, we can publish this information for either your internal shop or external suppliers that might be building your part. And we're going to use a lightweight viewable called a 3D PDF. We are going to use the Publish to 3D PDF on the MBD toolbar, and we'll use a predefined action engineering template that publishes the presentation states or 3D views that we pulled in, as well as all the attributes or the custom property information. And we're going to publish a BREP in a high quality fashion into that 3D PDF, as well as a step 242 file, because we probably want to enable geometry interoperability. So we save that PDF, and then anyone can actually open that PDF using the free Adobe Reader version. They don't actually need a paid subscription. They just open it using a free Adobe Reader. And as you can see, we've got the 3D PDF open here. It has the same kind of behavior that we saw in that native SOLIDWORKS model, except it's lightweight and nobody has to have SOLIDWORKS to use it. So there's our datum feature A identified with the flatness, including the bill of characteristic, balloon ID, which is really helping us identify from a human readable perspective, as well as a machine readable bill of characteristics. And that's how we complete the digital thread. Also remember that when we published that 3D PDF, we included a step file. So I'll show you where that is located in Adobe Reader. As you click open the paperclip, you'll see that step file, and then you can save that off to your local drive. And so that's available as well to enable interoperability. So how can we use 3D MBD data to close the gaps between typically separated silos of engineering, manufacturing, and quality? Early on, we're really wrapped up in the engineering phase, and we won't necessarily see dramatic cost savings. And this is why it's essential that we see manufacturing and quality colleagues as partners, because it's that collaboration that enables the major enterprise-wide cost savings that you're looking for. We've shown you some tools for using the digital thread and how to close gaps between typically separated silos. At Action Engineering, we have coaching and learning systems to help you and your users understand how to author proper MBD data in SOLIDWORKS. Thank you for watching, and I will pass the ball back to Sarah for our poll and Q&A session.
Thank you so much, Jennifer. We do have one last poll, and it will appear on your screen shortly. So we're just looking to see if have you considered geometric tolerancing and using DimXpert on the 3D model. So I'll give you a few seconds to respond. Okay, now we'll go ahead and show those results. Okay, awesome. So thank you everyone who presented. That was fantastic. We do have some time left for a question and answer period. So keep any questions you have coming. We have had a few throughout the presentation. So we have a couple all ready to go. So let's go ahead and get started. The first question I have here is for Rob. And it's, if you have features 1 inch below the surface part, how do they get measured?
So on a GOM system, absolutely what David has shown, a lot of the measurement happens on the exterior surface geometry. So your question related to things that are deep inside of a part, whether it be 1 inch or 2 inch, most GOM systems also come with a probe. So in our manual or semi-automatic systems, you could use a probe with that part, but for fully automated systems on the shop floor, you would not. Depending on the size of the feature, depending on how deep it would be in terms of accessibility, you may not be able to measure it. But it would really depend on things, but you can either use the scanner or the probe in those situations.
Awesome, thanks, Rob. Another question I have here is, does GOM doesn't support QIF?
No, it does not. Not that I'm aware of. That's a pretty new format that may or may not find itself in there one day. So you'd have to use something like Checkmate to be able to process that data.
Great. And I do have a question here for Kirsten. Is PMI required to utilize SOLIDWORKS CAM?
No, you can use SOLIDWORKS CAM. So the technology is going to recognize those SOLIDWORKS features as they were created. Certainly, if you have PMI data, it's going to help you if you want to use tolerance-based machining. But SOLIDWORKS CAM functions completely without PMI data.
Thanks, Kirsten. One more question for you here. How does SOLIDWORKS CAM integrate with the multiple CNC machines / types out there?
So SOLIDWORKS CAM is going to work with routers, lasers, plasma, water jets, vertical milling machines, horizontal milling machines, turning machines, multitasking machines, so such as mill turn. And yeah, it's an incredibly versatile CAM system. It's going to offer you 2.5 axis programming all the way up to 5 axis simultaneous programming. And in terms of SOLIDWORKS CAM standard, like I said, if you're on active subscription and you have 2018 or higher, you have access to that now. And all you would need is a post-processor to get that CAM solution speaking to your machines.
Awesome. And just one last question here. So my parts are significantly larger than the demonstration part. How does the part size affect all of the groups?
How does the part size affect all of the groups?
I think it was for Rob. Sorry, Kristen.
Oh, no problem. No problem.
I can answer it easily for a metrology application. So if your parts, so in the example part we've shown, the size of it was easy enough for us to put on an automated rotary table. For parts that couldn't fit on that size of a table, you can manually check those as well. So you don't have to put them on a rotary table. You can actually move the sensor around, whether it be on a stand or physically move the part. So it may not be as quick, but there are definitely solutions as your parts get bigger.
Fantastic. So I think that's all the time we have for today. Thank you everyone for joining us and staying for the full hour. If any questions do arise after we finish here today, please don't hesitate to reach out or reply to the webinar email that we will be sending afterwards, and we can be in touch. And once again, thank you to all of our presenters for such a great presentation. And thank you to all of our attendees for spending some of your Wednesday afternoon here with us. Please stay safe and healthy, and we hope to see you again soon. Thank you.
Thank you.
Thank you.